Welcome back to Advent of Code 2023, day 21. I'm a bit late, a whole day late, because day 22 is about to open, but I had a flight, so there's my excuse. Right. Let's... Okay, so if... I'm supposed to check out... I'm in a hotel right now. I'm supposed to check out in like 3.5 hours, so probably in 3 hours I'll have to stop if I haven't solved the problem by then. So it's a race against the clock. Alright, let's get started then. 21... Not 5. Not 5. 21. Step counter. Right. Just grab my coffee then. Okay. So what do we got? We managed to catch the airship right as it's dropping someone else off on their all expenses paid trip to Desert Island. Okay. It even helpfully drops you off near the gardener and his massive farm. Gardener? Oh, it's this guy. That was a tough problem, wasn't it? The seed planting one. You got the sand flowing again. Great work. Now we just need to wait until we have enough sand to filter the water for Snow Island, and we'll have snow again in no time. While you wait, one of the elves that works with the gardener heard how good you are at solving problems. And would like your help. He needs to get his steps. Pedometer. Okay. In for the day. So he'd like to know which garden plots he can reach with exactly his remaining 64 steps. Ooh, it's an exact distance problem. That's interesting. It gives you an up-to-date map of his starting position, S, garden plots dot, and rocks hash. For example, the elf starts at the starting position S, which also counts as a garden plot. Then he can take one step north, south, east, or west, but only onto tiles that are garden plots. Right. Okay. So you can revisit old positions. In this example, if the elf's goal was to get exactly 6 more steps today. Hello, Galvabart. You finished all problems up to day 21? I've finished all problems up to and including day 20. If that's what you mean, then yes. But I'm doing 21 now. I'm a bit behind because yesterday I had to take a flight. So today I'll try and do 21 and 22 because 22 opens in like a few hours. 64 steps today, and the map he's handed you is much larger than the example map. Let's have a look. Okay. Is that... makes a shape. It's like a Christmas tree? No. So there's an interesting gap around here where it's like diamond. Alright. Okay. How many garden plots could the elf reach in exactly 64 steps? So it's tempting to do brute force, just try all, well, like 4 to the power of 64 different paths. No, we need some sort of okay, I see the thing. So there's this idea of parity, right? So some steps you can only ever reach on an even number of steps, and some odd. For example, the starting position you can only ever reach on an even number of steps. Because it's like a chessboard. Let's imagine this as a chessboard and you got black and white tiled. Whenever you do a move, you go from white to black or black to white. So if we just label each position, so we do breadth first search. We find all places we can reach in 64 steps. The circles are the goals? No, they're just... in the diagram here, circles are just positions you could reach in exactly 6 steps. But there's no circles in the input. That's the map. You can walk on the dots, you can't walk on the hashes. So I reckon what we need to do is just do a breadth first search to find all the spaces which are reachable in 64 steps or fewer. Alright. And just label each of those with their distance and their parity. And then, for each of them, you can actually say... Then of all of those, you just take the ones which are on... which have parity 0, right? Or which have even parity. So if something is reachable in 62 steps, then it's also reachable in 64 steps. Just walk one space and walk back, right? Is there any other rule that I'm missing here? Okay. So yeah, that's okay. Let's try that then. So, we've had a lot of 2D grids lately, haven't we? That's good. I like 2D grids. When are we going to get 3D grids? I think he's done a couple of 3D problems in the past, but not many. 21. Oh, look at that graph for day 20. Beautiful. That graph helps so much. Okay, so it's another grid. So just should we copy in some of this stuff from before? We've got a pause. Wait, we want it to be data class. So, Galva Bart, are you... you're doing Advent of Code as well? How have you managed so far? Okay, so we don't need multiply. We need add. I'm only on day 3, started very late. Fair enough. The first couple of days are surprisingly they throw you off easily. You expect them to be super easy because in past years they were. They were harder than expected, but they were also like quantifiably harder than previous years, definitely. Yeah, I mean, I tripped up on day one so badly. Normally it's like a 5-minute day in previous years. But it was a good problem nonetheless. I mean, alright, so what do we want? Okay, so we got grid equals that, and then we want to just only on day 3. Oh yeah, so I don't know if you're on my leaderboard. It's not a competitive thing, it's just like nice to keep track of where everyone is, but if you haven't already joined it, I can if it interests you, I can post the code here in chat so that we can like see everyone's progress for all my viewers. So that gives us the grid. Well, where do we start? Oh, there's an S somewhere in there. If S in line, so we're gonna need to keep track of the row number, just so we can get the position. So if S is in the line, then start equals pause. So the row is going to be I, the column is going to be line dot find S, and then let's just get rid of the S. So that's just going to be a dot now. Okay. So where are we starting? Dot replace. Whoops, that's not how you use replace. It's got to be S like that. 65, 65. Where is that? 60. There it is. Is that in the center? Yeah, it is. Okay. Okay, so let's get the height and the width out of here. gotta start putting strings in my prints more often because I'm always printing numbers and then I forget later on what I printed, so that helps. There we go. See? Just put some colons in here. Let's be grammatically correct. There we go. Alright, so we know where we're starting. So we want let's define a pos method called getParity. How do we do this? We just say return self.row plus self.call sent to. So 0, 0 will have 0 parity and so on. So it's basically black and white chessboard. Yeah, that'll be useful. Okay, so we need to... Should we use yeah, breadth first search for given a starting location and a distance. Let's say a number of steps. Oh no, radius. That's the best term. Radius. We want BFS to return all the cells which are accessible in radius number of steps. Okay. So Q equals, so we're going to need a Q here. We need a distance table. And Q.put starting location. Dist start equals 0. Okay. Or should we make a getNeighbors method? Well, it's good to make this as a separate method because then we can have different neighbor functions if needed, if we need it later. So for delta in, so it's going to be pos 1 0 pos -1 0. So it's basically up, down, left, right, some order. Up, yeah, 0 1 pos 0 -1. What have I done here? Neighbor equals pos plus delta if so we need 0. We need it to be inbounds, so 0 is less than or equal to pos.row is less than n, and 0 is less than or equal to pos.call is less than m. Alright, so if it's inbounds and it's not a hash, so grid neighbor.row neighbor.call is not equal to hash, then we yield this as a neighbor. Alright, that gets the 4 potential neighbors. Okay, so breadth first search. We put start on the queue. We update the dist table. Okay, while not queue.empty current equals queue.get. Alright, so we get something from the queue. And does get also pop? Yes. But pop might be misleading, so they don't use pop, because pop normally means pop from the end. But Q, well, it is popping from the end, but it's popping from the front. Whereas if you pop in a stack, you pop, like in Python lists, you pop from the right-hand side of the list, like the most recently added thing. So I guess get makes it clearer that there's some logic here which is shifting things along using a linked list. Well, get is generic, because if it used a priority queue, then it wouldn't even be popping from the ends. It would be just picking out the item with the highest priority, lowest priority. So yeah, get is a generic term. It doesn't mean I think pop normally means just take from the ends, yeah. But queues you may not want to take from the ends. And get also does some stuff with parallelization as well, so it like blocks and stuff, so it's a complicated method. Alright, so we get something from the queue. I think we want to say, okay, for neighbor in get neighbors of current. Alright, so we're going to look at each of the neighbors. We know these are valid neighbors. If neighbor not in dist, we've never seen this neighbor before. So we want to update dist neighbor equals dist current. Hang on. If dist current is radius, we don't want to go any further, so we go to the next current. We go to the next item in the queue. So if we hit the radius 64, we don't want any more neighbors. All right. So now we know where we have fewer than 64 steps already. If neighbor not in dist neighbor equals dist current plus 1. Q dot put neighbor. That's everything. Don't need these spaces. And then finally, I guess we want to return the distance table. That tells us everything we need to know. All the things we found and their distances, right? So, dist equals BFS start 64. Let's see if this works. Print dist. Yeah, so it's kind of a diamond pattern. 4, 62, 6. Alright. That looks about right. It's quite big. Alright. And now what? We just want to choose all the ones that have the same parity as... Hello, Hair Football. Yeah, you get diamond shape. So yeah, that's what we would expect. And it's dodging around the obstacles. So now I guess we just want to pick all the ones which have the same parity as the start. Wait, no. All... Okay. Total 1. This is the answer to part 1. For... So we don't care about the distances here. We're saying everything is attainable in exactly 64 steps if it's the same parity as the start plus the parity of 64, which is 0, sort of. So we want for pause in dist.keys. So we want pause dot get parity plus start dot get parity plus 64, the parity of 64, which is going to be 0, but let's just, should we say r equals 64? Let's just not use magic numbers here. So that plus that plus that is 0. That means yeah, it matches the parity of what the parity should be after 64 movements from the start. Was that it? Print total 1. 3748. Oops. Where's the browser? There it is. Alright. First time, please? Correct. Okay, good. Lately, I've not been getting it right first time. Why are you adding the pause and start parity? Okay, so the logic here is the parity. So let's say, okay, so the start has a parity. It might be 0, it might be 1. In this case, it's actually 0, but it doesn't matter. We're making this generic. Okay, so start has a parity of either 0 or 1. Every time we make a step, the parity flips from 0 to 1 and 1 to 0. So if we take 64 steps, the parity will flip 64 times. So start parity plus 64% 2 will give us the final parity we end up on. Right, so that those two added together should be the parity after doing those 64 moves. And in fact, it would be better. We don't need it equals 0 here. It would actually be smarter to write this like this. It's the same, but this makes it clearer. Like that. I should have done that. Alright, so we want start plus r%2 equals, and we want that to be equal to the parity of the position. As long as that's true, then I believe you can reach that space in exactly 64 steps, because you can just go back and forth. So I wonder what they're going to do for part 2. I bet there's going to be rules on where we're allowed to move, because that will be nasty. Now, I mean, the parity argument doesn't quite work. The elf seems confused. Let's run it again. Yeah. Let's do that. 3748. 3748. Okay. So the elf seems confused by your answer until he realizes his mistake. He was reading from a list of his favorite numbers that are both perfect squares and perfect cubes, not his step counter. The actual number of steps he needs to get to today is exactly 26 million. He also points out that the garden plots and rocks are set up so that the map repeats infinitely in every direction. So if you were to look one additional map width or map height out from the edge of the example map above, you would find that it keeps repeating. Oh, fudge. Simulate the repetition, yeah. So we basically have to walk off the edge of... So let me just look at the example map. That is the example map. Okay. So, yeah. If you walk off, it would be like... The column value would be column 0, yeah. Okay, so we can update the neighbors function. So we could still do breadth first search. 26 million is a lot, but it's not too much. Oh, but wait. This is... $26 million steps in all directions will be... It's gonna be like the square of that, so that is too much. So we can't just do breadth first search. Love getting that silly little gold star. Hang on. But, I mean... 26 million steps, doesn't that mean you can go everywhere? Well, the parity is gonna... Well, depending on how big the map is, I guess the parity will flip when you go off the side of the map. Can we take modulo first to reduce the steps? Like, in this example, this tiny example, you can go everywhere, can't you? Wait. Oh, no, they mean... Oh, no, I get it. Okay. You can go everywhere within one garden, but on the outermost gardens, you can only reach certain spots. Interesting. Okay. All right. So it's really just a case of seeing what happened. Okay, so from S, if we have millions of steps, then clearly we can reach every spot. Like, well, parity-wise, we can't every other spot in one entire garden plot. Okay, and the same goes for this one and this one, but you got to figure out what happens just on the very outskirts. So at the outermost garden, you might only be able to reach a few. Oh man, how are we gonna do this? I definitely can't run breadth first search. Well, that many steps, because it's going to be basically that squared, that many spaces. Okay, so we have to analyze. We have to say huh. I think we probably want to find all, like, shortest paths between every pair of points around the edges of the map. Okay, conveniently, it's just dots around the edge of the map. That makes things easier. Then you don't have to worry about obstacles blocking the way. Like, once you reach a spot on the edge, on the outside, you can Alright, but if we knew the distance, the shortest path distance between every pair of points on the outside, and we knew the distance between every pair of points where one is on the outside and one is on the inside, right? Let's say we pre-computed all of that, which I think we can do in a reasonable amount of time. Then it's a case of okay, this is tough to think about, but I'm sure there's some really nice, elegant solution here. How much time do I have? Like 2 hours before I need to stop the stream, so we'll see how much I can do. So I feel like that's a good first step. We need to know kind of how to get to the edges from inside the map, and we need to get how... Basically, we need to be able to get from an edge to any other point on the map. If we know that information, that's a good start, okay? The shortest distance. Now, how do we use that to figure out how far we can get? So we would know... So if we had 26 million or whatever, we could say, okay, so it takes... The quickest path to the northern edge, let's say, is some X or something, I don't know. Alright. Then what's the... Wish you good luck with the problem. See you next time, Hex. Alright. Thanks for stopping by, Galvabat. I'll be on later today because we've got 22 opening as well, so I'll be busy. So once we get to the northern edge, we know how long it'll take to get from there to the next northern edge, right? What time is it where you're at? 9 AM. Normally, so the next problem opens at 12 PM for me. And normally I do it around 12 PM or a few hours afterwards, but yeah, I didn't do yesterday because I was flying, so trying to cram in 2 problems today. Oh man. Okay, so if we get to the northern edge, then what? Can find the shortest... I'll see if I can do 2 problems today, but this one looks like I might be stuck on it for a while. Can we work out how many grids we can fully cover? Probably. So don't worry about the edges, the fringe cases, but if we know how long it takes for us to get to any cell on the perimeter, then we can work out the number of steps to take to get, say we're going north, we can work out the number of steps to get to any cell on the perimeter of the northern block, right? So say it's like 1,000 or whatever. Well, it's going to be like a couple of hundred, let's say 200. At that point, you can just keep adding 200, and that will get you some number of blocks north. So you can just do arithmetic to work out how far you can get, right? So that kind of... How do we make this rigorous? Oh, I have some semblance of an idea here, but I'm not sure how to formulate it. So if we can ignore everything inside and just think about the borders, right? We can sort of work out the distance to get to border cells of grids far away, just using that knowledge. So don't worry about anything inside, because you can just walk along the borders, can't you? Once you get to the border, to get to borders far away, you don't need to go through, except it kind of helps, but like there might, like if you're standing here, is it quicker to walk around the edge? If you want to get to the top, is it quicker to walk around the edge or to go straight through? It looks like it's quicker to go through straight through. Yeah, it is actually. Fine, but we can iron out that detail. So okay, fine. So can I work out one point? What is the furthest point? Let's start with a simpler problem. What is the furthest point north I can get to? How do I work that out? I can work out how long it takes for me to get to any cells on this edge to start with, all right? Now, the path to the northernmost point I can reach, does it necessarily go through this edge? It doesn't make sense for... Well, yeah, look. Once you get to this side edge, right, then you can just go straight up along the side edges as far as you want. So the question is it quicker than going straight through? Well, for short distances, no. If I wanted to get to, say, on the grid that's north of us, if I wanted to get to this point here, let's say, then I would go up to this edge here, let's say to here, and then I would just go up, right? And that's the shortest path. However, if you're going millions and millions of grids away, you don't want to be weaving in and out of these hashes, because oh, well, see, my argument doesn't quite work here, because there is actually a column with no obstacles in it. This column, the column that S is on. Ah, look, and same horizontally. That makes things interesting. So S, you start, you can go left, right without. Ah, okay. So that means we already know what the shortest distance is to any edge. You literally just go vertically and horizontal. Ah, okay. He's done this on purpose. Similarly, you can use these diagonals to get around quickly as well, but that's not important right now. That simplifies things. Okay, so we just need to think in terms of the meta grid, which is the set of all these gardens attached to each other. Shall I... Alright, I have an idea. Let's create a set of checkpoints, one at each corner, and one at each middle of each row. Right. So there's 1, 2, 3, 4, 5, 6, 7, 8 checkpoints. Also the middles as well, I suppose, so 9. And we know it's a fixed distance to get between any one of these points. It's like you just go vertically or horizontally. Don't worry about all the obstacles in between. Right? Now, we can walk along this meta grid and see how far we can get in the huge meta grid. If it takes a certain number of steps, then we know what the furthest checkpoint we can get to is, right? So that's a start. So once we get to those furthest points, we'll know how much how many steps we have left over. So with that, we can then just do a simple breadth first search to find how many cells are reachable in on those edges. So we can get a set of all the reachable cells around the perimeter, right? So then what? Once we have that, that's it, isn't it? But then we need to know how many grids are fully covered. Well, that's kind of clear, but how do we code that? Maybe I need to get Microsoft Paint out to make this clearer. So I'm saying we basically got a grid that looks like this, okay? We've got a point here. Right, let's put crosses on them. Cross. Point here. We start here. We don't care about what's inside these squares, right? We know how far we can walk. Right, so we can go like this. It's just a big meta grid. Right, so we can say we know the distance between points, so we can get we can create a set which is all the points which are furthest away. Alright, so say it's like all the way over here, and it's going to form some sort of circle shape, roughly. Can find all the furthest points. Okay. What do we do with that information? Well, not only do we find the furthest points, but we also know how many steps we have left over. When we get to those points. So from each of those points, how many are there going to be? A lot. Well, let's imagine we need to do some number crunching here. So let's say we're going 26 million steps, right? And one of these edges is like well, it's like 60, right? So that's like, that is like 60. One of these little edges. So 26 million. Divided by 60, it's going to be in hundreds of thousands, I guess. So let's say we have 100,000 points. A couple of 100,000 points. And for each of them, we have to a leftover, which is kind of less than 60. Otherwise, we would have reached the next point further on. Okay. So from each of those points, we can just do a sort of a small breadth first search to find the reachable points around them. And this basically creates an outer perimeter a covering of cells we can reach, right? And it should fully enclose our area. Because it mustn't it? Because if we can reach here and we can reach here, there wouldn't be. Could there be a gap between them? Not really. Because from this point, you would be able to reach. I don't know. There's some steps needed to make this completely rigorous, but we can work out a covering in like 1 million operations or something. A few million. So we can do that. Once we have that, we know everything left inside this space is coverable. Right? So basically, we've worked out the full set of cells which are reachable in n number of steps, right? Oh, but then you got to do the parity thing. How do we do that? Because now it's not. We can't just go through them and add all the parities. We need to. Well, for a given grid, will the parity be the same in each grid? Let's have a look. So that's 130. The parity is not going to flip each time, is it? Let's see. So it's 131 by 131. So that's like 0 up to 130. So the next 0 is at 131. Oh. Damn. So it does flip parities when you move into the next grid. Oh, man. That's a pain. Alright, roughly how many grids do we expect this to be? We're going 26 million. 26 million divided by 100. Alright, that's gonna be like... It's gonna be like 200,000 in each direction. That's too many. That'll be 200,000 grids this way, this way, that way. So you square that and you'll get roughly the... So we can't actually build a perimeter. Come on, there's got to be... I'm not thinking in the right way, I think. I think there's got to be a cleaner way of doing this. We don't really want to build the full perimeter because that's too big. Well, no, the perimeter is not too big. All right, let's say we find the rightmost point, like this point here. So that's going to be about 200,000 across. We can do that. We can find how far we get. Okay. Now what? We can sort of do a walk around to get the perimeter. Can we? Yeah, we can. We can walk to find the full perimeter of squares that are fully coverable. We just walk around the edges, and we can do that. That's like 200,000. That's not too many. So we can find... Alright. Let's say we do that. We find a perimeter of cells like that, okay? Now what? We've got say, roughly hundreds of thousands of these points. We're saying that's the outermost edges. This is basically what we did before, okay? But we know these squares are fully coverable. And any other set of squares we can't add because they're not fully coverable. Okay. Can we now work out what we need to work out? So, if we were able to get that, then the two things we need to do now are, the first thing is do this mini breadth first search from each outermost point to get all the like the fringe edges to find out how many points are reachable within like just a few number of steps. Okay, that's fine. We can do that, and we can work out their parity as well because there's not many. But the last thing we need to do is we need to be able to count how many of these inner squares, and they're taking their parity into account. How many? We can do that. Look at it this way. For each column, we know the topmost square, its location, and we know the bottommost square. We know what parity... Do you need to care about parity? Well... I guess by symmetry... No, we don't, actually, do we? Because actually, it's a checkerboard, so... Oh no, it's not a checkerboard because of the hashes. Alright, so... What if you double the initial block? So... let's say this is the initial block. We double it. Jumping double it. Use a 2x2 block as the start. Yeah, then yeah, you're right. Then whatever number of... So if I have, say, S blocks, S cells of a certain parity here, and T cells of a certain parity here, then it's gonna fit T and S, and then it becomes perfectly symmetrical. So yeah. Now it doesn't matter how many. That makes more sense. So, so if I'm using that block instead, then what do we do? Just the same process. Figuring out the best angle to enter a block from. Entering from the right be different from entering from the bottom. Yeah, well, that's something else to think about. Well, okay, at least, okay, so this gives us a solution to working out the number of reachable cells inside our perimeter, okay, because now we know there's whatever, s plus t plus t, we know that number, we can pre-compute that number, and so it's just the same for every block. So if we figured out what our perimeter looks like, now it's just a case of so that gives us that number. Okay. That's the easier number to compute now. I think we're almost there then. So, will this method actually work? So this is our initial block. We pre-compute this block. We have our special points, which are the corners and the, I guess well, should we just stick with the corners? No, we need the we need the inner dots as well, because there could be spaces which are reachable from those points, which are not as easily reachable from the corners. I'm not sure. Okay, well, let's say we have all the points along the edge. The so it's basically 16 points around the edges. 16 special points around the edges. Okay. So the idea is we use basic arithmetic to work out where the furthest points are in each direction. And that gives us kind of where their blocks are. And then we can sort of work out the perimeter just by kind of walking around the edges and reasoning it. I don't know. Coding-wise, it might be a bit messy, but we can do it. Alright. So let's say we do that. Then we'll know... Then it's... The calculation for inside the squares is easy, isn't it? Yeah. Okay. We could do that as a first step. And then the next step would be, from each of these special checkpoints along the edges, we run a quick breadth first search and hope that that kind of covers all the remaining edges outside of our kind of rectangular perimeter. And just kind of add them all up. Oh man. I feel like there's some very strong symmetry here that makes all this redundant. I mean, yeah. Is it symmetrical? Hang on. We might be able to, like, cut out, like, 3/4 of this work if it's perfectly symmetrical. No, it's not. Just looking at the... It's not even rotationally symmetrical, I don't think. Doesn't matter. It's fine. Okay. Oh, man. Alright, how much time do I have left? Maybe about an hour and a half. So how do I want to get started? We've got this big quadrant block. That's a good idea. I mean, even if we stuck with the smaller block, we can still do it. It's just... You need to... It's not hard, it's just you need to just account for the parities. So if you knew the parity of the top and the bottom of each column, then you could work it out. Column by column, I suppose. Something like that. I don't know. Doesn't matter. We'll use the big quadrant. I need to think about this for a while. That light above my... I have to cover that light with my head, it's annoying. Oh my god, that diagram looks horrific now. Okay, every step of this process seems doable. Is there a catch? My worry is... well... So we're computing basically a Manhattan metric diamond, essentially, because we know... kind of on the bigger grid, so we know how many... I mean, the weird anti-symmetry, though, is that we start... well, okay, it doesn't matter. We start in the middle of this left-hand side, but it doesn't actually matter where we start, does it? Okay, so we've got this big 4 block, but we actually start around inside this top left block. Okay. Actually, you know what? I'm not sure whether I like doing this quadrant thing, because then it's kind of not symmetric, is it? Because if we're starting from this top left bit, then we can't reach as far to the right as we can to the left, so this whole big thing is gonna be... It's not as clear. It might still be easy to just go back to smaller block and just do the parity calculation. Like, we can figure that out. Yeah, I mean, if we're doing it kind of like a scan line way, we know in each column, we know where the furthest block we can reach is, and we know whether that's an S or a T, let's say, and then this one's a T, then immediately we know. Alright, we'll go back. I'm not gonna... I'll go back to what I was doing before. But I mean, I like the idea, but I'm just worried it just makes things less symmetric. So, if I go... Okay, let's do a new diagram. This is... looks ridiculous now. How do I just... Okay. So, okay, let's illustrate this again. We could actually use the square tool here. Alright, so we've got starting block. And it's basically, we know, pre-computing, we know how many cells are of parity 0 or whatever. Okay, so call this an S block. Alright. And like, using arithmetic, we can work out what the furthest full block we can reach is. Let's say it's up here. And it might be an S or it might be a T. Doesn't matter, right? We can work out what it will be. We can work out how far it will be. And that's the furthest full block we can reach. Because anything outside... Or we can work out if the corners are reachable. And from that... Wait. Yeah, we can work out if it's 9 point... If all 9 points are reachable, and if they are, then we know that the square is fully reachable, right? You would think so. Actually, is that even necessarily true? It's faster to walk around the perimeter than it is to go through, so what if we can reach this point here, but we can't reach this point here? But... is that the case? That could be the case. I wouldn't think so. Let's have a look at the... suppose it doesn't matter. This will all get fixed by the search we're going to do later on. Alright, so it doesn't matter. All we know is these are the furthest corner points we can reach, starting from S. So it's like 60 in any direction, for example. Alright, so we know roughly how far we can get. Alright, now what? And similarly, we can do the same below. Find the square. square with the furthest corner points. And that could be an S, it could be a T, doesn't matter. Alright. So we do that to begin with. And we have one column that we've figured out the furthest corner points we can reach. Alright. That's basic arithmetic, no searching needed. Okay, now what? So, once we've got that, and it's going to be like 100,000 blocks, I guess. For each of these blocks in this sequence here, we can kind of scan left and right to work out what the leftmost rectangle we can reach. So like, for like this next one, we can work out, say, the leftmost here and the rightmost here. And we'll know like what their parity is as well. Oops. So it's kind of like a two-dimensional scan approach. So we find this one column, and then from this column we then kind of spread to find the leftmost points of each row. So like this. Let's say it's like this. I mean, whatever. The coding will work this out. We don't need to know what shape it's going to look like ahead of time. So now we've basically got a shape. We know each of these corner points are reachable. And we know that there is no rectangle to the left or down whose corner points are fully reachable. So these are the kind of the furthest we can go via this process. And we also know, okay, so now we've worked out a proper perimeter. Okay. That immediately gives us the number of reachable cells within the perimeter. Okay, it's just adding up the parities for each column or whatever. We can do that. If we know this is S, we know this is S, then we know what to do with that. Okay. Is there any flaw in this? What I said earlier about whether this point right here is reachable from this corner point, it's not even clear. Let's say when we're working out the interior, we're ignoring the outermost one, so we're actually just working out all this stuff inside. Okay, so once we know the perimeter, we can work out all the cells inside. We can add them up, and we don't have to do much work for that. It's not searching, it's just arithmetic per column, per row, whatever. Right, so that's step one. Well, step two. Step one is find this perimeter. Step two, compute the number of fully coverable grids and add up the parities and whatever. Step three is then do a search from each of these corner points, make a full set of reachable points from each of these corner points. So if we include these corner points as well, but we don't want to cover points we've already covered, so it's like we're not allowed to go inside the interior. We'll have to account for that. So we look for all points outside the interior which are reachable, add those in as well. We'll know their parities because we're doing that in the FS. Is that it? Is that our algorithm? There must be a way simpler approach to this, but I can do this. We just start coding it then. Alright, so what are we going to do? Part 2. So the number we've got here is that. That's the radius we're using this time. Okay. So I want to start by finding the top two. All right. I kind of want to redefine the grid so that 0 is the starting point. So do we want to define a new infinite grid, and given coordinates we can use our current grid. Alright, so we want to create a new grid, basically. Let's say class grid. Should we just call it grid then? And I want to center it on the center of our starter grid that we were given here. So we'll give it a grid to start with. Oh, what am I doing? It's not what you do. Alright, self-grid. So we store that grid. Now we need methods. Define get. Well, given position, we want to get what is at that grid, right? So no, we want to be able to get a position as if we're centering on S. So we know grid and we know start. Okay. So the location in our inner grid is going to be... So if I'm asking for 0, 0, for example, I want to get what I want to get what's actually at the start. So we add the start location. So adjusted pos equals pos plus start. So if I ask for 0, 0, the location in the inner grid is actually going to be 60, 60 or whatever. 65. It doesn't matter. But we might be asking for something kind of beyond the grid size, so we need to... So that's going to be a pause. So we need to scale it down with modulo arithmetic. So... So this creates an infinite grid with a base grid. Adjust to pause equals pause plus start, and then we want so it's going to be a new pause where we've got adjusted pause dot row percent width dot height and then we want the call percent width. What do we do with that? We say well, no, we want to return self.grid that row, that column, right? Let's test this out. So we've got I don't want to call it grid anymore. It's now, should we call it plane? Like XY plane? Plane equals, all right, let's call it plane. We're creating a thing called a plane rather than a grid. So we create a plane, print get, all right, let's try getting pause 0, 0. Print lane.get. It's a dot, alright, yeah. I mean, okay, let's just try a few around to make sure we're getting... So if we do... just try this one and the one above it. We should get dot and hash. So we've got 1, and then we've got -1. Dot hash. And now let's try adding 130. So we want just, let's go to the right by 130. Add 130 to each of these. So it should be dot hash dot hash hash dot. Oh, it's 131. Tell you what, it's better if we just write it out fully. 131 0. dot hash. Yeah, okay. I think it's just make sure that this works fully. So I'll just say, just try some huge number. Yeah, okay. Alright, I kind of trust that. So we've now got a notion of a plane. Alright. And it's centered on 0 now. Centered on the S. One second. I ran out of water and I'm too lazy to go out to the supermarket, so I'm gonna buy water from my minibar. Let me just make sure it's not a ridiculous price. So it's gonna be 1,000 dong. 10,000 END. That's 30 pence for a bottle of water. That's fine. Okay. I normally avoid minibars, but... that's fine. Alright, okay, so I can make myself a coffee, because I'm gonna need it. Right, where was I? So we want to get the top. Oh man. Okay, so we need to write down some numbers here. So the distance to the top of this square is... Well, we've got to remember as well that these corners don't coincide, so... I gotta go back to paint. We need to make sure I've got these numbers right. Alright, so I'm saying, so the height here to this point here is kind of like, I don't know, let's call it H, because it's 65 or something. Alright. But then there's a point just above us which starts the next grid, right? So if I want to work out the top right corner here, we walk to the right until we're on this corner. Okay. So that's another H, because it's a square. So it's H plus H. We're now at the corner. We've used H plus H steps, 2H steps. Alright, so we've got 2H that we've used up. And now we want to find how far we can, how many we can reach using our allowance. So if we're walking K squares up, let's say we're walking K squares, the number of cells would be the full height of one of these squares, which is 2H, right? So it's going to be K times 2H. So basically we're going K plus 1 times, it's supposed to be a plus. Right, this is 2H to get to the top right corner. I'm trying to find the maximal value of K, which won't go over R. R being the maximum amount of steps we're allowed. So so we need that bit to be less than or equal to R. So kind of K plus 1 is less than or equal to R over 2H. And that's kind of integer rounded down. So then 1, take away the 1. That's floor. Alright, so K we can set to be equal to... Alright, let's plug this in and see if it makes sense. Alright, so so K equals, so I'm saying, what was it? Int of, so it's going to be R divided by 2 times, alright, so H equals start dot pos. Alright, so that's kind of the mini radius. Start, what, not start dot row, I mean. K equals int of R divided by 2 times H minus 1. Alright, so that, hope all this arithmetic is correct, so print K. Is this going to give us a sensible number? 203,855, so I'm saying the topmost corners are going to be at top corner right equals pause. It's going to be so the row is going to be minus h and then minus k times 2 times h, so that many blocks. And the column will just be h. Does this make any sense? Let's see. Two 6501215. So it's just slightly less than R. Which is right, because it's just like 150, so takes 2h, which is 130 to get to that corner. Then we go another that many rows. Okay, that sort of makes sense. Okay. Now what? Let me get my coffee. Okay. So, got that. Can do the same for the left. Now what? We can do the bottoms as well, why not? Do we need to be doing this? What are we using these values for? It doesn't matter. Let's just write it so that I know it's there. So, it's going to be positive, negative. Okay, fine. So we've got the corners. From this, we can now work out the man. This is so confusing. But conceptually it works. I mean, according to Microsoft Paint, it works. Wait, at this point, do we need... Oh, we don't need to compute these corners. We just need to compute the furthest height we can reach. So the furthest height we can reach... Furthest... height is that, basically. Or let's store the positive version. We're just storing the absolute value. So we don't need these right now. Okay. What do I do now? Well, don't think in terms of height. Let's think in terms of blocks. Well, it's actually K. K is the number we like. So, for k equals 0, that's like where we started. And k equals this number here, that's the furthest block we can reach. And the row number of that block will be k times 2h. highest block equals block height equals, I don't know, let's just say it's hang on, let me look at what all these blocks look like. I see. All right, so K. All right, let's put some semantic meaning to this. K actually means num blocks height. It's saying we can go that many blocks high, we can go that many blocks up, we can go that many blocks low, and in each place we'll be able to reach all four corners of this block. All right, that's what we know so far. All right, okay. So let's create a hash table which maps. So for, let's say I in range, so starting from, let's say, minus num block height up to and including num block height. So we start at the top block and we go all the way down. So we know each of those blocks are fully reachable, or the corners are fully reachable. We want to extend left and right to see what the left and rightmost are. Right. So let's create a hash table. Let's say horizontal say num block horizontal. So given a number of blocks, we want to see how many blocks we can go left and right. Let's just go right arbitrarily because the left is the same by symmetry. Okay, so I mean, we don't need to, by symmetry, we can just go from 0. Right? Because it's going to be the same. So let's say we go 1 block down. Let's say corner. Alright, I need paint again. Right, what am I trying to do now? I'm saying, okay. Oops. Just paint with... No. How do I... That just removes... Where's... Okay, paint tool. How does that have to be? Big, and I want it white. Or should we just do a filled... box, white color. Okay. Why isn't it filled? Why is this so difficult? Solid fill, there we go. Just make lots of... There we go. Okay, okay, okay. Okay, right. So I'm saying... if we go down so to an arbitrary block, say this is 0, this one is k, right? So for an arbitrary one, let's say I, which is what this for loop is doing, I know where the corners are. I want to find the furthest block to the right. Okay. So I know that this corner here is at it's gonna be, it takes K, no. I plus 1 times 2h steps to get there. So for 0, it's going to be 2h. And for I, it's I plus 1, 2h. Okay, so that's how many steps we use. So what is the furthest corner I can get? It would be basically we're trying to count how many 2h's we can do to go to the right. So it'll be R minus, so we do R minus that. That's how many steps we have left, divided by 2h. So that's it, isn't it? So if we couldn't move any blocks, then it would be... R would be quite small. So we wouldn't have many steps left, so we wouldn't be able to even do one lot of 2h. So yeah, that's right. Okay. I should not be doing this in the morning. So num blocks horizontal for this I value equals what is it? So it's R minus, so it's going to be I plus 1 times 2 times h. That divided by 2 times h. Alright, let's see if we actually get a table out of this. Yeah, okay. So, to begin with, so at the start, it's going to be like... Yeah, that looks about right. So if we go that far, we can't go any further. 203855. Yeah, that makes sense. So if we go that far, we can't go one more block to the right, because otherwise we could go one more block down. And then each of these is 1, 2, 3, 4. I mean, did we need to do this? It's a perfect... Of course it's a perfect diamond. It's perfectly symmetrical. Why did I... Oh, my brain is not good at this time. It's a perfect diamond. So we don't need to do this, really. Whatever. But it doesn't matter. I mean, we can do this. All right, fine. Whatever. We need to know the perimeter points, okay? So... Hang on, there's so much symmetry here. What will be the leftover when we get to the top corner? It'll be some number. Let's say we've used so-and-so steps to get there. Then we have, I don't know, say like 20 steps left. But it's going to be 20 steps left at every other corner as well. It's going to be the same. Alright, this is... I'm seeing all the symmetry now. So actually, this cuts out a lot of work. So let me try and make that clear. All right, so we found the topmost rectangle. All right, we know we can reach each of these corners, but furthermore, we know that if we go there, then we have, let's say, x steps left, and x is less than 2h, right? And this forms a perfect diamond. I don't know why I didn't realize this before. Of course it does. Oh, the reason I didn't realize this before is because I wasn't centering. Now we are centering. I was doing it where it was slightly offset before, and then it's kind of weird. Okay, we're centering now. Okay, so we perform a perfect diamond. But what's interesting is that each of these corners is still... If we get to that corner, we still have exactly x... left over, isn't it? Yes. And if we get to this corner, we have 2h plus x left over. Right? And that's the same for each of these corners. So we've got all the perimeter points. This point, that point, this point, that point, this point, that point, and so on. All around here. And it's x, 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 2h plus x, x, 2h plus x. Alright, we've got all of that. So what do we do with that? From that, we can do... We only need to do breadth first search like once, and then we've got the pattern. like everywhere almost, but not quite, because it's you know what? Do these 2h plus x matter? That's quite a huge number. If we look at the actual graph, with 2h plus x steps, we can probably reach the whole of this quarter here, which would make it not matter. So let's just use the x's. Alright. That simplifies things. So we've got all the x points. Now what do we do with that? Shall I just do a fresh diagram here? Now, if I were to do breadth first search from one of these x's, we would get a radius of points round like this, right? We can exclude the ones that go back through this grid. And that will give us a set of new points. I need a new diagram here, clearly. Alright, let's start a new diagram. Alright, simplified. We've kind of simplified the situation. Alright, so this is the starting point. This is where we start. That's H. So we know this is the furthest. Let's go in the positive I direction, so... Hang on. Start again. Alright, so we go... This is the center. This is the furthest down. This is the furthest right. Okay, so that's a positive I, positive J. Okay. And we know that there's a perfect Manhattan shape. That's not good. Let's try and right, whatever. The point is for each of these points, we can do a breadth first search. We can get the number of reachable cells. So if this is the middle, excluding this line here, so we want to get all the cells which don't touch this line, but do touch this line. Does that make sense? I'm getting confused again. Okay. We can afford to do a bit of extra work here. We can compute all this stuff. So we know basically the perfect diamond, right? We've established that. Furthermore, we know... God. That... can't draw this easily. I'll just put dot, dot, dot. Bigger dots, please. So we know these corner points. Right, we know exactly where they all of them are. We can just build some table, some set with all of these points. Right, and from them... Oh, and we know these points as well. Okay, how about we just run a lot of breadth-first searches then? From all of these points, collect a huge set. One big set of all reachable points. Right, we can do that. We have enough computation time. Because it's not symmetrical. The number on this side isn't... This top left side is not going to be the same as this. Because these squares don't have rotational, symmetrical, any kind of reflectional symmetry. So we have to do this all separate. Alright, fine. We do that. We compute the full set of reachable points. Okay. But we don't go within these squares, so we've got to have something in the getNeighbors function to make sure we don't... We avoid... How do we do that? We only ever need to run the breadth-first search from these corners, don't we? Because that will give us the ones from these corners anyway. It will use 2h to get there. And then the extra x to get a bit further. Okay, got it. Alright, so we record all these corner points. For each of them, we give them an allowance of 2h plus x. X being whatever amount of space we have left. That's fine. For each of those corner points, we then just run a breadth-first search from there, but we're not allowed to go off the grid, which is easy because our breadth-first search is already designed to do that, right? Breadth-first search has an inbounds checking, so we're checking within one grid. So that means we only have to do it once and then multiply that number by whatever. But what about these cells down here? Interesting. Okay, we might need to do... Okay, I think we have to use these points as well as probably this point, these end points, because we're not accounting for... You know what? There might actually be a simpler way than all of this nonsense about parity and all this stuff. Okay. Let's say we just simplify this. Just take all these corners. We want breadth first search from all of them. Doesn't matter if we go in, we go out, whatever. We just accumulate all these cells on the boundary, right? Okay, I've got that. That's the first step. Got a huge set with all these cells. We know their parity, we know how much they contribute, we can add in that total. Then to get the interior, it's really, for each row, you just take the rightmost here, the leftmost here, and then you know how many cells are in between them. What's more, you know the parity of this one and you know the parity of this one, so you know how much parity contributes, alright? You don't need to start recording the parities of all these things. Okay. I think I might have something here now, finally. It took me ages to get here. That works, doesn't it? Alright, I don't know. Let's try. Alright, so what would I need to compute again? I would need to compute these corners. And that's it, basically. Just record. And yeah, there's some symmetry here, like you could just do one and then multiply it to get all the rest, but I think we have enough time to actually compute all of them. We'll see. So okay. So we've got the top block. We know where its corners are. So let's create a set. Perimeter corners. So for each block, we want to add the corners, all 4 corners. Let's just add all 4. Don't worry about trying to cut corners, literally trying to cut corners. Just put all 4 corners in there. Right, so for I in range 0, num block height. Num block. Alright, so we don't do this. This is how many blocks we go across. That's how many we go down. That's how many we go across. So we want to add perimeter corners dot add. So the top left will be hang on. Just get the origin, the center. center equals, so it's going to be pause, so it's going to be, no, go back. So the center of this block we're talking about here is going to be pause of I, so it's going to be row I, column that, so it's going to be I times 2 times H num blocks horizontal times 2 times H. Is that right? Okay, and then the perimeter corners. So that's the center of this block. So then so we need to flip the signs as well. For SI in -1, 1, or SJ in -1, 1. Top left corner. Perimeter corners dot add the top left will be center minus pos HH. So just go, well, yeah. Top right corner. Let's add pos minus H, that makes more sense. So this one we're gonna add minus H plus H. Then we got bottom left, center plus H minus H, and bottom right corner, center plus HH. So that's 4 corners, and we do that for welcome back to Advent of Code 2023, day 21. We need to finish off 21. So just a reminder of what day 21 is. It's tricky, but maybe with a fresh mind and a fresh cup of coffee, I can give this a better attempt. Ow, ow, ow. Sorry, my apartment only has glass cups instead of coffee cups. So I could ask the host for one, but it's such a minor thing to ask for. Ow, 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 ow. All right. Yeah, so we've got this situation where we've got this grid garden where you can walk out around the edges, and Um, we start at the center. We've got obstacles. And I've just realized something. Hang on. Oh, no, okay, that's fine. Yeah. Um, One property that we had of the big input was that we could walk down the middle, right? Except I never actually verified that that was true. Is it actually true? It seems to be, but at the same time, the sample input, it's not true for. So it's maybe I shouldn't try to write my code especially for this. What we do know is that there are empty spaces around the edges, but not necessarily across the middle. So basically part 2, we've got this grid where we're stitching together lots of gardens. In an infinite grid, we're trying to find how far we can get in this big old map. I'm a bit concerned now because right, we'll try and write it for the generic input, because if I was writing it where I assumed you could go along the middles and the middle row and the middle column, but let's not assume that, because otherwise I won't be able to test it easily on the sample. But okay, so trying to find how right, we need to figure out some things first. First of all, I want to know if every cell in the map is actually reachable. We're not doing 22. Because I think there might be some like little gaps. Should we just focus on this small input? It's just easier to deal with. So right here, every cell is accessible, but that may not be the case in the big input. So we shouldn't assume. That was one mistake I made before. Another mistake I made before was just some numbers I got wrong. For example, 2h. Why was I using 2h? What's h? H equals start.row. Why did I do that? That was wrong. It's not 2h. It's n. nm. What's going on here? I equals 64. Okay, okay. Plane. I don't want to use plane anymore. Let's hide that for now. Yeah, hide that. H is wrong. So we got 11 by 11. That makes sense. The start is the dead center. Okay, fine. It's me. Okay, so all right. All right, all this stuff let's start fresh. Okay, so just comment out this stuff. All right, so it's just what's going on? BFS. Why isn't it doing BFS? Okay, get part 1 working again. List index out of range. Start radius. Radius 64. Could still work for 64. Get neighbors. It's failing here? Huh? But don't debug. This is as I left it last time. What's going on here? What was the last 10, 3? Okay. This is trying to go over the edge, right? Oh, for goodness sake. That was wrong? That's not good. That was wrong all along? How did it work before? Okay, somehow it worked. 42. Alright, and the answer is... For the first part, the answer is... Oh no, but you have to use... Six. And the answer should be 16. I need to change the number here. 6. 16. Okay, fine. Okay. Alright, so part 1 is fine. I would say... If there's no radius supplied, we just, we just run through the whole thing. 16. So I want to see what it's like if we don't supply a radius. Well, okay, fine. 42. That should be the whole map, right? It's 11 by 11, 121, but we halve the board. Oh, but then there's the hashes and all that stuff. Okay, fine, fine. Alright, so part 1 is fine. So where do I go from here? Okay, so let's go back to paint. So let's do the numbers correctly this time, because last time I actually got some numbers wrong. And so we've got a grid with this, okay. It has height n. It's actually square, but yeah, okay. Right. So then we got grids above and below, so on. All right. So we want to find so as before, we want to find the furthest grid such that we can reach the corners of it. But can't reach the other two corners. Does that make sense? So so we start here. Wait, is that what I want to do? Hello, Mara. So late? It's not that late. It's only a couple of days. I mean, I didn't have time to finish this one off yesterday. So let me start this diagram from fresh, because I think I got some things wrong in my diagram before. So we start here. So I'm trying to think whether we want... I had a plus shape with the S in the middle, that was the key. Yeah, so I was using that property before, but now I've realized that the small input, the small sample, doesn't have that property. And so I kind of, even though it's a useful property, I'm not sure whether I want to, because I still want the method to work on this. The sample. Like, did whatever you did still work on the sample? because the sample doesn't have a plus. So if I work without the plus, then I guess I'm looking at corners. Alright, well I'll try to make it work generically. So that means I think I want to deal with corners rather than anything else. So then if I'm working just with corners, then it's more about well, what is the first point I would enter this square? Well, in the big input, it's probably going to be here. In the center, because of the plus. The plus really makes things easier, doesn't it? Let me... Yeah, because on the sample input you have to go kind of windy. Maybe I should just assume the plus then, because if I don't assume the plus, then it's not clear how, at what point on the furthest square I'll actually enter the square. I could work it out by... Oh, but it'd be messy. I mean, you could try working out all distances to all points on those square, but then that doesn't necessarily... Okay, whatever. We'll assume the plus then. So that means we can go straight up, enter that point there. So, and we'll know exactly what remainder we have when we get there. So with that we can do a search to find out how much further we'll get. So let's say hang on, so the first entry point is going to be in the side, but the one just to the side, like this, and the one just to the side like this, the first entry points are going to be the corners. So there's basically two types of things we're going to have to check for. That's fine, we can do that. And so I can run a breadth first search from this point, I can run a breadth first search from this point, and this point, and then these ones will all be the same. So So we enter here, here. So we only have to run it once and then multiply it by the number of these. And then when we get to here, it's sort of, I mean, it's symmetrical, so it's going to be like we enter here, and so on. So there's basically 1, 2, 5, 6, 7, 8 breadth first searches we need to do. Now the other thing is the parity. What parity will this one have? And whatever parity it has, it will be the same across the entire diamond here. So that is to be taken into account as well. The parity of the first square, let's say, is 0. Oops. Is 0 because it's like starting square. So we can work out now what that will be. Alright, so what is that location? Where is it? So we need... Hang on, so let's say this is K grids up. So that's K times N to get from the middle here to the middle of here, right? Yeah. So to get to just the edge here, it's going to be Kn minus is it n over 2, like the rounded down. To get to here. To that point there. No, don't. No. Oh my god. Bigger. No, I want black. I've clicked white. Why is it doing black? I don't remember how paint works. Why is it black? I've selected white. What? White. What the heck? Oh, this is primary color. I forget how this works. This is secondary color. Primary. Yeah, I forgot. Huh. Alright. Okay, so it's Kn minus n over 2 rounded down to get to that point there. And we want it to be such that that is maximal. So we've got Kn minus n over 2 is less, strictly less than our big number, r, let's say. We're trying to pick the biggest n such that this holds. Or less than or equal to? No, if it were equal to, then... Well, yeah, it could be equal to. That's fine. We can land exactly on that space. We can do that too. We just have a remainder of 0. We're trying to pick the biggest n such that's true. Okay, so k will be r minus n over 2 rounded down divided by n. So that gives us the formula for finding k. Just calculate that. Just set it equal to that. Okay, so that tells us how many squares we are away. Should we just work out now what k is? Because that'll tell us whether it's odd or even. And it'll tell us what remainder we have when we get there. So the remainder we have will be oh, it'll be r minus k n minus n over 2. Okay, let's work that out now. I want to see some numbers. Alright, part 2 fresh. Or I'll start doing it here. Okay, so r is that number. Alright, we'll use the big input then. Oops. Forget trying to do it on the small input. That's... Okay. We've got just less than 3 hours until the next problem. Well, let's see if we can do this. Alright, so... part 1, was that correct for part 1? 7566? We're doubled. Hang on, no, because I removed something. Put it back, put it back, put it back. And that should be 64. 3748. Correct. Okay, fine. So, part 2. R is that. Right? We know n. We know it's square, so we don't need to use m anymore. N is that. 1 through 1. So n. Yeah, okay. So we want k equals so what did I get from paint? K equals r minus n over 2 floored, alright. So it's r minus n over, it's going to be n over 2. And then just floor division of n. Okay. So, I mean, so what would be the parity? The parity, so is basically whether k is odd or even. Let's see what k is. So if k is 0, we don't move at all. So it's even. Well, that makes things simple. Oh, it doesn't make things simpler or harder. It doesn't matter what it was. Okay, so so the parity, it's basically has the same parity as the starting square, which is nice. That means we can use the same results from the starting square. But it doesn't really matter anyway. Alright, so that gives us that. What is the remainder when we get there? So remainder equals... So it's going to be R minus... Kn minus... So it's going to be K times N minus N over 2. Wait, print remainder. Please be small. Then I don't have to worry about weird stuff. 130? What? That's a pain. It's big, and it goes right to the... So basically we can reach as far as, like, the end of this grid. Okay. But that means... that I was hoping it was small, because if it's big, that means we can... Okay, we can go as far as just to the last... the top row, but not further. But it also means we can go off the sides. Okay, fine. Okay, so let's try this using this information then. So we want to work out what... So when we reach that grid, we then want to see how many further cells we can reach just in that grid. If it's 130... This does make things more complicated. Fine, whatever. Alright, so, we want to get BFS start radius equals none. Shall I do the parity? So parity just be 0. Non-default parameter follows whatever. What the? Alright. So if I've got the parity, so BFS just returns a number. We don't want to return the dist, so we want to return the for pos in dist.keys. we want to return how many? Return sum of dist dot keys, sum of so we want this basically the number of keys that have the same whose distance is, so it's going to be k key plus parity key d no wait we just take the values because those are just integers. All right. The distance percent 2 is parity. That's what we want, right? We want to count how many have the same parity as just our parity variable. So we don't need to do all this. We don't care about all the distances and all that stuff. 3748, okay. Yeah, that's the better way to do it. So BFS doesn't return all those distances, we just count. In fact, that's fine, we can do it this way. Alright, so we want to know here in part 2 print, so I'm interested in knowing, so we want BFS so the location on the grid is going to be row, it's going to be n-1 column, create a new name for this, mid, where's mid? Mid equals n over 2. We're going to be using this a lot, so column is mid. Parity is going to be 0 because it's the same. Let's be absolutely correct here. K percent 2. Radius is going to be remainder. That's how many steps we have, 130. Alright, so I want to know how many are reachable in that square, restricted to that square. 566. What? No. BFS, pause, n-1, mid, remainder. Five, 6, 6, 1. Oh yeah, because it's really big. Oh, yeah. That's about right. Okay. Wait, so what's the total number of reachable squares? Let's try this as well. Just remove the radius. We'll set it to remove the radius altogether. 7509 is the total number of reachable squares. What would it be if the parity was different? 7509, 7566. Interesting. So there's actually obstacles. There's actually unreachable squares. I think I knew that already. can't find them, but they're probably lurking around somewhere. Or it's just because of the obstacles they don't get as far. Doesn't matter, we trust the numbers. Okay, so that is how many are reachable in that square. Alright. So basically we have to just do this in a for loop in the right way to get all the different locations. Now the problem is let's go back to the paints. The problem is because it's 130, which is really big, that means we could go up here, could go to the side here to get to this corner. And we've got to deal with this square as well. So then we'd have about 60 left, so we can get like, I don't know, like here, it's this stretch of area. So here we can get like pretty far. All right. And then here this corner? What remainder do we have here? Well, actually, would we not cover this fully? I don't think so. No. Hang on, 130. So we can reach here. Oh, I see. So it goes like this. So actually, we've got different types of squares here, but it does follow a pattern. Like this. Oh my god. Right, well, basically we know how many of each of these there are. We just need to count them up. And then that brings us down to here. Alright, so the number of different types of BFSs we have to do. We have to do one for this top one. That's 1. 2 on the... So there's 4 on 4 corners. And then we've got these weird ones where we've only got a little bit left. Okay. So how many of those do we have? So that finishes here. And how far do we get here? So we'll basically get like this. So that's K, isn't it? There's K of them. Alright, well, let's just do them one by one. Alright, so and fill in the numbers here. So let's start with the corners. The top, the left, the right, and then the bottom. Alright, so top equals BFS on that. Bottom equals BFS. So if we just use similar numbers, it's going to be 0, mid. K to remainder. Left equals mid n minus 1. If you say m minus 1, try and be generic in case it's a rectangle, but most of this doesn't make sense if it... We'll just stick with n. If it wasn't rectangle. And right, mid, 0. Okay. Don't need to print remainder. So that gives us the 4 corners. Right. Now, let's deal with this type here. Okay. So that one. We start from the bottom left corner. And the remainder, how much remainder will you have? There'll be, okay, whatever remainder we had when we were here. But we can add in n to get to here. And then subtract mid. Hang on. All right. So whatever let's say my remainder, this is my remainder while I'm sitting here. If I add n, I get here. So I could start from here with remainder plus n, and then we subtract the n again. That means we start from here, and now add in mid, and that means I'm allowed to start from here. All right. So I'm saying it's basically remainder plus mid. What? That's too much. Wait, that means this square's fully covered? I'm getting so confused. It shouldn't be... No, that's correct. That's correct. Remainder plus mid doesn't go... The maximum... To fully cover a square, we would need n plus n. But this is n plus n over 2. Okay. Okay, got it. Got it. So, we start from the bottom corner. So that's whatever it is. And we do remainder... okay. Let me just start coding this. Alright, so it's this new one. Let's call it top right inner, because there's also an outer, equals BFS. So we start from n minus 1, 0, it's the same parity, isn't it? Yeah. K percent 2. So this time it'll be remainder plus mid. So we have a bit more allowance this time because we're starting in the corner, pulled back a bit, so we can reach pretty far. Okay. So then we gotta do all the other ones. Bottom right inner is the same, but we start from 0, 0. And then we've got top left inner and bottom left inner. So top left will be n-1, n-1. And bottom left will be 0, 0, n-1. So you could do a for loop here to make it cleaner. I'd rather just write them out than... Right, so let's just start adding these up. So total 2 equals 0. So once I've got the corners, we want total 2 plus equals, so it'll be just top plus bottom plus left plus right. Okay. Now this one, we do total 2 plus equals, so it's going to be, we add these up, but we have to multiply. Welcome back to Advent of Code. It's Christmas Day, and that of course means lots of coding, as every year. Hello, Amara. Well, I feel like I'm really close with this problem, but maybe there's a slight... Oh, thanks for the raid, Irish champ. What were you just playing? Or doing? If you're playing a game, then this is a very different kind of stream. I'm gonna be coding some very mathematical stuff. I even have Microsoft Paint graphics. Right, let me bring up the Microsoft Paint graphics. GoldenEye New Vegas. Oh, nice. I think New Vegas is probably the longest game it ever took me to finish. Actually, no, I think it was The Witcher 3, and then New Vegas is second. All right, that's my Microsoft Paint graphics. I don't know if you can make any sense of that. I don't think I can anymore. But that's basically what I'm trying to calculate. I seriously, I used to have a tablet for writing stuff. Now I'm just trying to do it using my mouse. I never even finished Blood and Wine, and I keep trying to go back and finishing it, but I always feel disconnected from the story now. If there doesn't seem to be a way to reset a DLC specifically, so you can just start a DLC storyline from scratch. Because if there was, I'd do that, but... Because there's been a big update to The Witcher, hasn't there? Now, like, graphics-wise, like, a big graphics update, so that would be interesting to... Let me just grab my coffee. Let me start the music as well. Alright, so where were we? Yeah, so I got this horrible mess that I'm trying to calculate. You can play the expansions on their own? Really? Is that a new thing? Because I thought I tried to do that before and I just couldn't, so I had to kind of try to remember where I was, and it's not a big deal. I could probably watch some YouTube video with cutscenes up to the point where I am and then carry on from there. So I think what I really need to be doing is using the... Whoops, wrong window. Sample case, but obviously we can't... We can't quite solve the sample case because it's a different format. It doesn't have that line in the middle, but we could write a brute force for the sample case and then use brute force to generate something a bit bigger. And that's basically our sample case. Make our own sample case. Do that. So... I'm gonna do that. I need... Let's see what happens if we just plug the sample in. I know it's going to be wrong. Just want to see what number we get out. So that's the sample. Run program on the sample. We get 6. What? Oh, but we need to change R to be... $5,000. Not this one. This one. One 167485556. And their one is 167333044. That's kind of promising. It means we're in the right magnitude, but because they've got obstacles and everything. So either I rewrite my program to... No, I really don't want to make it generic. I want to take advantage of the plus thing. Okay, in that case, I have to work out what it should be for if I modify this sample case. So if it's dot, 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 and dots along this row. So how am I going to do that? Let's we need to be able to do breadth first search infinitely. So we say get neighbors, pause, infinite equals false. So if it's false infinite is true, then we want to do equals We want to always use modular arithmetic to get back into the grid. Roll over the grid on the other side. And then, so if infinite, then do that. Is that right? Yeah, okay, so my God, there's a lag when I'm typing. It's so here we don't need to change anything here except for the get neighbors. The only thing that changes is the get neighbors method. Right. So if we're doing that, then after all this, we want to just run breadth first search from the start to okay, so the start to the with the parity 0. Well, no, parity is going to be alright, try this. Steps equals 16. Alright, we'll try each of the numbers. So parity is going to be 16. No. Parity is just if we need to flip the parity. We don't need to flip the parity. Radius is steps. Infinite equals true. So print BFS start parity equals 0, ready equals steps. Okay, so hopefully that will give us what? 42, which is wrong. This is our brute force method, and exactly. No, not 16. 6 is the example we want to look at. 16. 6 gives us 16. 6 gives us 16. 10. Okay, that's correct. 10. 42. Damn it. The answer's 50. So, I mean, there's something wrong with our brute force. Sorry, not brute force. BFS stands for breadth first search, not brute force. Because if there is, that could be the problem, and the problem is being realized in every single one of these calls. Q dot put start, this start equals 0. Wow, not Q dot empty. So Q is a Q, okay. Current equals Q dot get. If this dot current is radius, continue. For neighbor and get neighbor's current infinite. So neighbor not in dist neighbor equals dist. Current plus 1. Yeah. Well, apparently there's something wrong with this BFS then. This is the grid. Return, basically count how many distances have the same parity. Oh. Parity should be steps, but that doesn't actually matter because it's even anyway. But yeah, it should be steps. That's weird. Parity should... Okay, whatever. So I'm missing a few. Let's try check the get neighbors method. So infinite should be true in this case. But delta in pos1 neighbor equals pos plus delta. If we're infinite, then we modulo down, so if it's already within the grid, that won't matter. Okay, and this check will be redundant if we're infinite, but that's fine. Check it anyway. If grid is not equal to hash, so in exactly 10 steps, Oh my god. So I'm missing 8 spaces. Start. What's start? Should be 0, 0, right? Oh. No. Start is printed here. Yeah, 5, 5. Can't go very far with 10 steps anyway. 1, 2, 3. Should we just print the distances and see what we've got? Right. Comment out all this other stuff. Five, 5, 0, 4, 5, 1. I'm just gonna have to check these by hand, aren't I? Alright, let's have a look at this one. 1, 10, 10. So we go 1, 2, 3, 4, 5, 6, 7. So that's now we're on row 1. Column 10? So we're on 6, 7, 8, 9. Column 9. One 10? That's 110. Oh, that's rotate. That's don't move things around. This one's 5, 6, 7, 8, 9, 10. 110 is that corner there. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's correct. Only a couple of hours left. Yeah. Hello, DJ. 1, 2, 3, 4, 5, 6, 7, 8. Why haven't I got minus numbers? Do I have minus numbers? How goes? Oh, I'm trying to... Why is S5 and not 6? Because it's 0 indexed. Oh, okay, because the IDE does it one indexed. So everything you see, you got to subtract 1. It's really annoying. I wish there was a way to just change the line numbers to start from 0 for that purpose, but I can't find one. So it's 5. S should be 5, 5 in programmatic terms. It's odd that an IDE wouldn't start at 0 since everything's in computer science. Not really. I think line numbers is... Nah. Line numbers you do start at 1. Like, if I say to a programmer, oh, you've got an error on line 20, it is done by 1. That's just the convention. So it's correct to start from 1. It'd be nice to have an option to change to 0 for... But then I guess this situation that I'm doing is not a normal situation. But yeah, we do index line numbers at 1. Alright, so one mistake here is we're not going off the edge of the map here. In fact, we're not going off the edge of the map at all. We're supposed to be. So 42, that's just within this square. Alright, so my infinite grid is not working. Infinite equals true. Radius start one CUDA active neighbor and get neighbors. It's all relies on get neighbors, so get neighbors. Pause, infinite equals, we've set it to true. Neighbor equals pause plus delta. Neighbor equals... Ah. Oh no, this is wrong. Because we actually want to keep... Why did I do it like this? We actually want to keep... We don't want to modulo it. We want to keep the big row in the column. We only want to modulo it for the purpose of checking this. That was wrong. Okay, so if infinite or that. So if it's infinite, we bypass this check. Otherwise, we and then we have to do this. Set n or set n. That was okay. So yeah, we're not modifying the neighbors, so the neighbors should be going off the edge. So that means I was replacing, I don't know, it was doing some nonsense. Try that now. 50, good. All right. So the full example we want to try. And I was hoping that was a bug with my BFS, because then that would be the problem, maybe. With the big example, but no, it was a problem with the infinite calculation. Alright, so we've got 6. 6 gives 16, 10 gives 50, correct, so far. 50, we should get 1594. Correct. 100, we should get 6536. Also, stop printing all this stuff. Uh, 500, 167004. Okay, now it's starting to slow down. 1000. Because it's quadratic, so it's gonna, for 1000, it'll be going over like 1,000,000 steps, won't it? Well, let's just make sure it's fully correct for this example. 668,697. Do we want to go to 5,000? That's too much, isn't it? I can try running it, but I think this is too much. This is going to be like 30 million or something. Alright, it'll probably finish within a few minutes. So, while I'm doing that, okay. So we've got a brute force approach, essentially. Not brute force, I've got to stop using that term. Breadth first search on the infinite grid. And obviously this won't work for the big example, but we can use it to test against our big example here. So this whole thing can be wrapped up as a method. So let's wrap it up as a method then. So we want So we want get num. Get num what? What is get num reachable? Whatever. For a given. Oh wow, it's slowing down like crazy. Whoa. I should have put a counter or something. It'll be a nice confirmation that this actually works. This infinite grid. All right, so get num reachable. We need a radius. That's it, isn't it? Radius is the only thing we need. Then everything comes from that. We'll call this result. Yeah, we don't print that. Turn result. Also, this could be condensed a bit. We can say, well, don't do that yet. Let's just wait till we see some numbers first. Get num reachable R. Don't print anything for now. So try and find the smallest example this fails on, and then try and figure out from there. Should be quite small, because if there's a problem with my BFS or something, then... Also... Hang on. What? No, that's fine. Yeah, it looks a bit weird, but that's fine. Well, we'll find out soon enough. Um, 5,000. 5,000 times 5,000 is, what, 25 million. That's not too bad. It should finish soon. 25 million. Because 1,000, 1,000 is a million. So it should just take 25 times longer than the last one. So how long did the last one take? Like 10 seconds? I don't know. Maybe it'll take like 5 minutes. We'll wait a bit. Because it won't go as far as that. Because, well... Because of the obstacles, but... There's a lot of overhead with this queue, I suppose, if we're putting lots of stuff in it. But it's designed to handle... whatever. Hello, Observer Herb. It's burning. Yeah, I could probably roast chestnuts on my over my laptop for Christmas. Have you been doing any more of these Advent of Codes? Oh my god, yesterday's was an absolute ordeal. Like 6 hours of trying to do linear algebra. It broke me. And in the end, I saw, yeah, yesterday's problem was brutally difficult, but most people solved it just by using like a Z3, which is Microsoft's constraint solver. It's just very powerful. You just plug in constraints and it just solves constraint problems, like linear constraint problems, like, I don't know, x plus y is less than or equal to so and so on. There is a way of solving it using maths, but my linear algebra isn't strong enough. But Z3 solves it in a second, so it's pretty cool. I mean, it's a good thing to learn as well, Z3, because some of these Advent of Codes, like, if the objective is just to get the answer, then I have no qualms using Z3 to do that. It's not counted as AI. Because it's behind the scenes, it's just using steepest descent type methods to get the solutions, but more advanced than steepest descent. But yeah, Z3 is pretty cool. In fact, I can show roughly what my code looked like if my IDE isn't going to crash. Day 24. It's very, I mean, I'm using the Python syntax, the Python module. So import Z3 solver. So here you create your variables, your unknowns. So I created the 3 position variables and the 3 velocity variables that I wanted to find. And then I plugged in another 1,000 constraints based on like the speed and the time that we know. So it's like, and then you add, so you create a solver, then you add each constraint to your solver. So in this case, it was kind of like a distance time equation. 1 for x, 1 for y, 1 for z, and then this was done like many times. So there are probably like 3,000 constraints in there. And then you just get model, and then it just does it all. And then you get the root, i.e. the integer values which would make all these constraints true. And it doesn't need to be like a linear equation, because this isn't linear. This is a non-linear equation, because you got times. You got here. You got a unknown multiplied by an unknown, so that's quadratic. So standard methods won't work. But yeah, no fuss. Just gets the answer. I could have used that for part 1 as well, but anyway. But part 1 I used linear algebra, but it wasn't too hard. Okay, it doesn't seem to be giving me the answer. I thought 25 million should be... I don't know. I thought it would be done. I'll give it a few more minutes, maybe. But yeah, today is the last day of Advent of Code. I'm finally free to switch to coding game, which is now running. But that'll run for another 2 weeks. Well, I say finally free. The final problem releases in 2 hours' time, just under 2 hours' time. So I need to finish this one before then. I don't need to. I can just skip this one, but then I'll leave a gap, which is free to start 2020 AOC. That's true. I need to catch up on all the archives. I've got 2020 and check. Oh, I gotta do 2019 and 2021. I've already done 2020 was the first one I actually did live. That was when I discovered Advent of Code. Oh man, 2020. What was this like? Interestingly, he didn't do any assembly code problems this year. I guess he's finally decided to have mercy, because last year I had this maybe 1 or 2 assembly code problems. The one that I caught up on 2018, that had 3 or 4 assembly code problems, and they were quite brutal. I don't think this is going to get an answer. Okay, well, I don't need it to run on 5000 because we kind of trust our program now. So the next step is to get unreachable. I'm leaving it running until the moment I want to actually run new code. Okay, so let's try some small number. 16 for now. And we want to be, should be, see, look, this is the first time I'm actually doing proper software engineer practices. I'm writing tests. Imagine doing that. What happens with code? Was so it was uh-oh, it's best practicing. We're gonna be here for another 6 hours. Get unreachable steps. Alright, we start small. We want to find the first point of failure here. So was goes on a finite grid, but it just does, wait, where's my paint program? My paint diagram. It does that. Uh-oh, OBS is throwing warnings at me. Encoding overloaded. Okay, probably need to stop the program soon. We're doing that. Does that make any sense? It doesn't to me anymore. But yeah, that's what our program is. We'll find out what's wrong soon. Alright, stopping the program. Okay, let's let my laptop cool down a bit. Right, so, okay, 16. Try that then. Should be... Oh, but no, okay, this is... We need to modify the input to be our format. We're expecting it to have dots along the central axis and dots along the horizontal. And that's the whole point, reason why I'm doing this. Okay. Try that. Oops, 24. How did you slip into there? 21. Should be 216, was 206. Interesting. Go smaller. Should be 63, was 59. Go smaller. Should be 7, was 17. 2 steps, really? Should be 4, was 23. Wait. How did you get more for 1? Then 2. Oh my god, wait. 0? Should be exactly 1. 22. Get none reachable steps. What the heck? We're not using any hard-coded variables, are we? Mid. Alright, we've got n equals 11. Start is that. Mid will be 5. So all right, let's go through these. Get num reachable. Top. Print k remainder. Remainder should be like negative. Remainder 0. Oh wait. You said this R if k equals 0. No. No. Why did I do this? It's okay for it to be negative. Take that out. Was minus 15. What? Hang on. Remainder 5. R is 0. Oh, I see. Okay, that was right. There's a weird situation where if you're starting in the same grid, you're not starting from the same position as you would be if you're starting from the neighboring grids, because when you start from here, you start in the center. But if you start from any of the outer ones, you start on the edge. That's just a weird thing. So that's fine then. So remainder should be 0. That's fine. Okay. K is 0. That's correct. Corners. There should be no corners. Everything, we're staying in the same grid. So we shouldn't be getting any values here. Top, bottom, left, right. 1, 1, 1, 1. BFS. Pause. Ah. It's the same problem. Okay, if K... Okay, let's look at the horrible diagram. If K is 0, there's no corners. Right, if K is 0, then it's just this square here. We should not have this big star shape. In fact, we should not have any of these things. Now, if K is 1, we would have corners. But we would not have these side edges. If K is 2, actually, K is 1, we would have the outer side edges, we wouldn't have the inners. If K is 2, we would have both outers and inners. Alright. So... if K is greater than 0, I mean, that applies to all of this, doesn't it? So... that whole thing is if K is greater than 0. Alright, try that. Was 47. How did we get more? Alright. Squares. So now so that shouldn't add anything. So I think the problem then is here. Alright, let's have a look at the evens. Print even. The even squares, which should just be one square, shouldn't it? 47. Oh! I'm fully searching this square. Hang on. Okay, I got it. I think my whole algorithm just isn't meant to deal with the situation where K equals 0. So we shouldn't be trying to fix it for that. It's meant to be the case where you can fully search your current grid. Alright, so let's not worry about this. Just... yeah, let's undo my changes. Okay, just only use examples where you can fully search your starting grid. Because what we should be doing really is just resorting to brute force for that situation, because it's just a small grid, so there's no point trying to do this remainder thing. Okay, so that's fine. Just use a bigger number then. Right, steps equals 0. Okay, so we want to... how many steps do we need to fully search this space? 1, 2, 3, 4, 5, 6, 7, 8. 7, 8, 9, 10. Looks like it's 10. Is there any weird caverns? It's probably 10. Alright. 10 is probably the minimum we should test. $82? Oh no, yeah, because... Alright, try 11 then. Should be 103, was 87. Okay, that's interesting. So if it's 11, one, two, three, four, five, six, 7, 8. Oh no, go back to 10 then. 10 is needed to fully search our square, so 10. We need to get it working for 10. Alright, k is 1, remainder 4. So that's saying when we get to the neighboring grid, we should have 4 steps left over. 1, 2, 3, 4, 5, 6. Yeah, and then we would have 4 steps left. That's correct. Should be 90, was 82. Okay, so we're just missing a few. That's, if we can find this issue, then maybe that's it. Alright, so K is correct. 1. We only go to the upper, the left, the right, down. We don't go any further than that. Top. Right, try printing these numbers then. Top, bottom, left, right. 8, 8, 10, 9. So let's start with top. 8. So they're saying if we arrive in this grid above us, so we would actually appear at the bottom here on the next grid, we would have 4 steps left. So how many steps can we reach in 4 steps? 1, 2, so it's 1, 2, 3, 4, 5, 6, 7, 8. Basically, I'm counting how many cells are within 4 spaces of us, but only counting the even parity ones. So it's 1, 0, 2. Hang on. So I have 4 steps. So we can go as far as 1, 2, 3, 4. So we can go on this row, we can go as far as 1, 2, 3, 4 there. So how many is that? 1, 2, 3, 4, 5. Right, on this row, we can get just these spaces. We can't get any further. And from there, we just get this one here. That's the only even one. That's 6. And then from this row, it's just these two. 7, 8. 8, correct. Okay. What's the next one? Bottom. Oh no, that was bottom. No. Bottom means we come in from the top. So it should be similar. So as before, on this row, 2, 3, 4. Wait, what? 1, 2, 3, 4, 5. So there's 5 on this row. Six, 7, 8. It should be. Hang on. Let me change all these. So we start from here. We can get to here. We can get to here. 1, 2, 3, 4. If you get to here, 1 to here. Go here. Can go here. Can go here. Can go here. 1, 2, 3, 4. 4. There's actually quite a few spaces we can reach. So it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Also, I think I counted the bottom wrong. Let me do this again. That's how many we should be able to reach. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It should be 11 from top and bottom. Why have I got 8? Right. Well, there's a bug. How much time have we got? We got 1 hour, 20 minutes to finish this. Alright, let's just focus on one of these. Top. So I started from this position. I used this parity. I used this remainder. And I got this. Okay. So we started from 10, 5. Correct. That's the starting point. K plus R, 11. We're saying it's odd parity. Uh-oh. Oh my god. Should be using a remainder, not R. R is the big one, the big number. The whole point of this is to divide out all the intermediate squares and just end up with a remainder. So remainder should be attributed to the parity, not the... See, this is bad the way I've done this. We shouldn't have to be putting a remainder. Remainder should just be factored into the BFS code. Because it's just always used, isn't it? But whatever, let's just try and fix this. Does that mean every single... Yeah, see, this would have been fine if I didn't provide a remainder. I just... Maybe I should do that, because you need to use mid here as well, don't you? Yeah. Okay, hang on. Get rid of these. Whatever remainder is... It should be taking it from the remainder field. We don't add it manually. So here, A plus R minus 1. See, that's... What is that? Take that out. K is the only thing which matters with regards to parity. It knows the rest. And then here... That's fine, because... Because we are starting in that square. Okay. So in the BFS code we need... the parity... Okay, we just do this. We just add the remainder in here. Okay. int and none type. Radius is none. Oh yeah. Just say if radius is none, just make it some huge number. That means I want to fully search a grid. We shouldn't be doing this. We should be giving an explicit value for the radius because we need the parity from it, don't we? So we shouldn't be doing that. And when we're calling it without a radius, we should actually just be giving a radius. So this is position, parity, radius. Okay, so just give the radius to be r. Here we can just say 0, here 1. Alright, that was a bunch of changes. Is that going to help? Should be 90, was 82. Okay. Fine, let's see if we can... Okay, so we're using k now. Wait, so print k... Still getting 8 here. Hang on. 1, 2, 3, 4, 5, 6. The parity doesn't change. Uh-oh. Why have I assumed the parity changes? Because... Because we're in a different position. So that all the parities are flipped, aren't they? If we are in this position, our parity is 0. If we are in this position, our parity is odd. But if we go one space up, it's even. So actually, the next one along has the same parity as the start. The next one along has the flipped parity. So on. Oh my god. So... Does that mean every parity is flipped? So the corners should actually be even. I think every single parity is flipped here. And then everything else branches out from there. Hang on. So these ones, inners, definitely have the same parity as the corners. Outers should have a flipped parity. Why is it still k? Alright, we'll leave it as k now. I've got so many mistakes all over the place. The even-filled squares... Now that's correct. That starts at 0 and all the evens are 0 and all the odds are 1 because we're starting from... Well, no, is it? No. It's the same logic. Okay, so this one is 1. This one is 0. But let's... Okay, so all the even squares which are not my starting square, we have to flip the parity as well. Everything is flipped. All the parities are flipped. But the one thing I need to add in is the starting square. This one is the only one whose parity doesn't conform to that flipping pattern, because the starting square we start at 0, 0. So, mid even. 0. Oh, okay. Alright, this actually matters as well. We can't start from the middle here. We've got to start from, let's say, 0, mid. 0, mid or something. It doesn't actually matter which side you do. They're all the same. It takes an even number of spaces to get from one side to the other. Wait. Okay, this is going to give me the correct answer for the corners. Oh. We got 90, but wait, there's still something that's bothering me. I think because we start at the corners and not the middles. That means we don't actually flip the parity for these because we're starting at the corners. Yeah, so that's still correct. So actually, most of these were correct to begin with. It's just it was the corners and the squares down here. Let's try this. Should be 90 was 90. All right. 11. Should be 90 was 103. Oh, come on. Why should it be 90? Oh, because now you're looking at the odds instead of evens, so it's different steps. Parity. These X's aren't going to mess things up, are they? Take the X's out. No, because we checked for hashes only. Okay, so put 11. Okay, so look at the top again. So top, we're saying k equals, yeah, k plus 1. There's a way to fix this parity thing and not have to worry about it so much. Just take the position into account as well. So instead of... So let's say we don't actually want this to mean parity. We want this to mean num grids. How many grids we've stepped away. And then we calculate the parity here. Parity equals... so it's going to be essentially num grids plus radius plus yeah, okay, just do that. %2. Just use that here. That's not changed anything, but okay, so I think we should just be giving k always. That's just number of grids we've walked away, except for the outers. So just change this. So yeah, the inners k, the outers k plus 1, because those you step one more. The evens that's fine. No, that should be 0. The odds 1, starting square 0. Okay, try that. 87, close. Did we break it for 10 though? Probably. Oh, we're back to 82. It's never ending. But think there was a suggestion somebody made to eliminate parity from this whole thing by basically pasting 4 grids together in a quadrant. And that means you got odd, even, odd, so then the parity kind of gets eliminated. I could have gone down that path. I'm very close though, I think. But the problem is parity logic, we don't want to feed in to the input. Let the parity be figured out here. So the parity is not quite right here. Because we're not factoring in the pause. Ah, okay. So the parity should actually be adding in the start dot row minus mid plus, it doesn't even need to be absolute value. Start dot col minus mid. So that's saying if we're not starting at the center, we're starting onto the side or the corner or whatever, the parity needs to be adjusted as well. Parity 0 means you start from the center of the grid. So if you're starting here, you need to flip the parity accordingly. So it'll be odd. And if you start from here, you'd flip the parity to even. Okay. As long as we add in this and this, that should just do it. Let's try now. There we go. 90. 11. Wrong. Okay. That might not be the whole issue though. That's a good start though. So now for K, we only ever provide the number of grids it takes to get there, and let the BFS work out the parity. Wait, no. Hang on. We don't really need to do this because we're trying to find... Oh, I see another problem now. It's the filled squares. Because some of them you start from corners and some of them you start from edges. Oh my god, so what do we do then? This is such a mess. Okay, I think first of all we don't need to add that in, forget that. Because that's already taken into account by the fact that we're starting at this position with a given radius. So that it should All right. If we know we're so and so number of grids away, then it's going to be maybe it's better to, instead of saying number of grids, just say steps to get here. If we knew that, then that's everything we need, right? So let's just plug in the full amount of steps. So steps to get here. How many steps we took to get here? How many more steps we got left? Add those two together. That's our parity. No. Don't think so. No. Okay. Parity should just literally just be radius. The problem is, I think I'm feeding in the wrong radius. Because if you arrive at a cell, I'm forcing myself to arrive at the bottom edge, right? And I'm saying the remaining steps is so-and-so. That encodes the parity in the first place, so... So let's just get rid of parity altogether. We'll just, it's just messing things up. Parity equals radius percent. Two. Okay, so let's just make sure the radius is correct. I think that's the problem. So if start radius infinite equals false. Okay, so start, get rid of the parity radius. Yeah, just get rid of the parity altogether. I think it's just been confusing me. All that matters is the radius, the starting space and the radius. That gives us everything, surely. Radius should be R here. Radius should be R. So here, it should be R plus 1 because no, this thing is gonna be have to be changed slightly. Don't worry about this for now. Starting square. Okay, take this out of the thing. Okay, try running that now. Oh no, that's changed our should be now. For goodness sake. Why did that change? Right, so we don't need this anymore. Just go back to what we had before. Radius percent to... BFS is giving us the wrong... This one is giving us the wrong answer now. So we give start, steps, infinite equals true. Maybe that's right, because this is not the sample. Oh, I see. All right, let's try test on the examples again. So, the example looks like that. And we want to try small numbers. 6, 10, 50. Try these. Steps equals 6. Don't worry about the was. We just care about the should be. 16. 10. 50. Correct. 50. 1745. Huh? No. 1594. Yeah. Okay, fine. So yeah, that's correct. Okay, so take out the gaps. So we trust our BFS now. So when I run this, no, steps 10. Should be 90. Alright, we trust that. Was 44. What the heck? Okay, fine. Now, let's look at these things one by one. So, the corners. BFS, pos, n-1, mid, remainder. So mid, result, top. Okay, let's check. So we're saying the top, we're saying this should be 11. The remainder is 4, correct. Top 11. So we're saying when we enter here, we have 4 spaces left. So we can go here, 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 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Correct. All right. So I trust the corners. All right, let's just block that out for now. Top right inner. There shouldn't be any inners. These should be zeros. Wait, should they? No. There probably should be inners. Yeah, there should be. Okay, so inner, we would arrive at the... So let's say the top right inner, or the bottom right inner, we enter that cell there with how many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. Inners should be empty. There shouldn't be any inners. Remainder plus mid. Ah, no, k minus 1. K is 1, so that's 0. So that doesn't contribute. Oh, yeah, okay. So the inners, conceptually, they have an amount, but they shouldn't contribute. Okay, that's correct. That's fine. The ones that should contribute are the outers. So let's have a look at the outers. That would be k equals 1. So we get 0, 0, 0, 0. That's actually correct. Because 10 spaces, we can't actually get to the outer spaces. We're just one short. We're two short, actually. Okay, and then the even filled squares. All right, this is where it's slightly wrong. So, there's two different types of even filled squares, as if this couldn't get any more complicated. There's the ones where we arrived on a corner, and there's the ones where we arrived on a side. The ones where we arrived on the side are the 4 new ones we add. So, so we do result plus equal. So it's going to be the ones we add on the side, the corners. All right, first of all, let's change this whole thing. Go from 2 up to and including k. We don't skip any. All right. So the 4 spaces we add at the top, left, right, middle are going to be BFS. Start from the mid. With radius, let's say. Okay, so the question is, what will the what would the radius be when we get there? I'm gonna have to finish soon. I see. The problem is I've been forcing them to start on the edges, but you can't always start on the edges. Or you can. Alright, let's just start in the middle. Mid-mid. And the radius will be R minus N times I minus 1. So if we move, say, if I equals 2, then we're moving into the second space. So we've moved n. So it'll be r minus n steps left over. That describes that. Don't need that. And then we add in the starting square. Do we even need this? Yeah, because the 4i minus 4 doesn't work for this one. So we say pause, mid, 0, R. Okay. No, just R. We start from starting space. Alright, try that. Should be 90, was 90. Try 11. It's gonna fail, isn't it? Should be 103, was 103. 12. 125. Alright, let's start 24. Please. 457, 457. Looks like this could be correct. Come on, let's go for something bigger. 412. Oh my god. Alright. Go for the big one. So we're gonna have to change to the big grid. But now there could be changes to the big grid that might make this not work, but hopefully I've made it correctly generic. I don't know. Okay, k equals that, remainder equals that, yeah, same numbers before. So now, the only bit which should take a long time is this. Because we're doing... $100,000, 200,000 BFSs, but they're restricted to the grid. So it's, I don't know, 200,000 times, well, that is quite a lot. I was doing this before, though. I guess the reason it didn't take long before is because I was only computing it once and then flipping. So I can actually cut that corner again, but the way I was cutting it before was wrong. This is correct, but it's taking a long time, so if I can compute beforehand, that's why I splitted it into odds and evens. Let's see if it finishes. So it's basically trying to do okay complete searches of this grid. So that's too much, isn't it? But we know it flipped. Okay, fine. Go back to the evens and the odds. But we can just say even. Let's say even equals so when I is even, it would basically just be this. And when I is odd... Okay, stop. It will be this. Right. And now we don't need to factor I in here. We just say if I percent 2 is 0, result plus equal even. So we only do this once, and then we just add in odd. Why'd you just space out like that? Okay. I need to go back to the previous sample just to make sure this works. So let's go back to 200, let's say. We don't use num. Just make sure we haven't got the even and the odd the wrong way around. Okay, promising. So now we're not doing all those BFSs, so don't do the should be, that'll take forever. There we go. Is that right? Got half an hour left. Oh my god, it's a Christmas miracle. Oh, bloody hell. Oh, I was going around in circles and circles and circles and circles with that parity stuff. Parity. At the end of the day, I didn't need to be being so specific about the parity. The key really was just to factor it into the BFS and not try to specify the parity as an input. Like that's see, that was bad practice. You don't try to do, if you have a method which does logic, you don't try to pre-compute some logic and then put it in as the input. Bad practice. You give it all your knowledge and let it do the logic. That's what its function is. Well, this testing helped. All right, well, in half an hour we'll have... Okay, so let's have a look at my stuff. Private leaderboard. 4 of us are all caught up. Umaro here is caught up as well, so the moment the problem releases... Hello, Sand Knight. Merry holidays. And it's supposed to be a holiday, isn't it? This is actually the most work I've done. Man, I've done more programming than I do when I worked as a software engineer. When I was a software engineer, it would be like, I don't know, 3-4 hours of programming, and then the rest would be like meetings and stuff. But this is the most work I've done in a while. Oh man. Okay, so it's because you are a mad lad. Yeah, everyone who takes part in this ridiculous event, Advent of Code, is crazy. Is a mad lad. So Eric, Eric, the guy who made this website, well, he actually he made a talk. I think it was at Google or something about Advent of Code. Let's see if I can find it. Eric Wastel, Advent of Code. I recommend watching it. It's oh, he's got several videos. Oh. Yeah, is it this one? Yeah, it's a good talk. He talks about what his findings are because when he first started Advent of Code in 2015, he anticipated only about 50 people signing up. Because he thought he has a few friends who are programmers and they've got friends, and he thought it would end there. But but in the first year he had thousands and thousands of people signing up, and it just grew to hundreds of thousands now. Let's see. Okay, so the day was 21. Wow, look at this. Okay, this is unusual. So the fastest guy took 14 minutes 35 seconds to solve it. That's at the high end. Normally people solve them, the top coders normally solve it in minutes because they've seen all these problems before, all variations. They've got pre-prepared libraries for all kinds of stuff. So if it takes them as long as 14 minutes, that means it was a hard problem because they actually had to sit down and do some maths for a change. The top 100 people took 1 hour 19 minutes. That is long. That is really long. That's probably the longest out of any of these days. Normally, the top 100 people solve it within an hour. Yeah, Omaro's been catching up. Omaro's been using a game engine to solve these problems, which is interesting. For some problems, it lends itself well. I would say for most, it would... I mean, for me at least, it would be harder than using Python. But naturally, everyone solved the first part 1 quickly, but that was a nice, easy part 1. So I'm about to start the next one in half an hour. I suppose I can take a break and try and find some food quickly before it starts. So yeah, this is Captain Coda's leaderboard. Captain Coda is a fun streamer to watch. He is a teacher in programming and stuff like this. And yeah, his Twitch username is the Captain Coda, in case anyone wants to check him out. But he usually will stream in about 5-6 hours time, so I usually raid him. Alright, Sand Knight, thanks for stopping by. The final problem, day 25, will release in half an hour. That's when I'll do the final stream. Final Advent of Code stream of the year. But all my VODs will be on Twitch, and I upload my videos to YouTube as well, so if you ever wanted to watch them. I mean, this one I wouldn't recommend watching because, my god, it was like 6-7 hours of me just banging my head against a wall. Some people like watching that stuff though, so... Some people are masochists. Because for some reason I'm still getting hundreds of views on my YouTube videos, even the ones where I'm just stuck trying to do linear algebra for like 5 hours. So yeah, apparently people like that stuff. But yeah, Spoof is often in my chat. And Smab UK. Spoof is a mathematician as well, I think, so he's often takes the mathematical approach. What else did I want to look at? This 21. Yeah, so that indicates a reduction in percentage of people who completed part 2 compared with part 1. It's going from here 75% down to 50%, and then it's 75%, 75%, 50% for 24. 24, bloody hell. That was bordering on unfair because it needed actual linear algebra knowledge to solve it. Which is fine. I mean, there's no boundaries. If he wants to make a problem which needs linear algebra knowledge, then fine. If you don't have certain knowledge, then you just got to go out and learn it. That's part of what Advent of Code is about. Alright. I don't have much food in my fridge. I can't really just rush to the supermarket to get some. I've got some dried anchovies in a tin somewhere. Alright, I'll stop there for now. Take a quick 20-minute break, and I'll be back in 20 minutes for the final day, which we pray is a nice easy one because it's Christmas Day, and I think Eric himself did mention that, you know, if he gives a hard problem on Christmas, people will spend the entire Christmas day, you know, they won't even go to see their families, they'll just spend the whole day solving these problems, so he usually gives a reasonably easy one for Christmas Day. But yeah, I recommend watching this talk as well, it's quite nice. He gives some insight into what people do in these problems. Oh, no, I've not seen this one. Okay, this is a different talk. The one I've seen was a talk at Google or something, I don't know. Oh, this one. This is the one I've seen. Yeah. But yeah, it's good insight into what he did to keep up with the trends, what worked, what didn't, what people liked, what people didn't like, whether he decided to keep the stuff that people didn't like because he just likes torturing us. It's good talk. Okay, this video I haven't seen before. Alright, anyway, enough. I need to take a quick break. And I'm gonna have to stitch that YouTube video together because that's now like 20 gigabytes of footage of me just doing nothing. Just scribbling in Microsoft Paint. But it all, for posterity, I'm uploading it all. The whole thing. I'm not cutting corners. People can watch the whole thing if they want to. Alright, thank you for watching. And see you in 20 minutes. So, bye-bye.